now.
Okay, I will paste the question. Okay, so your task is to construct a directed graph from an undirected graph that satisfies given constraints. So for this problem, the constraint is that given a connected undirected graph and a vertex in that graph, construct a directed graph from the undirected graph such that any path in the graph leads to that particular vertex. So for example, because that was kind of wordy, so you're given an undirected graph here on the left right here, and so let's say the input vertex is 1. So you will be converting the graph so that it's a directed graph, so that any path in that graph leads to 1. So like, as you can see here, this was an undirected graph, and then we converted this into, and we passed, this is an undirected graph right here, and the new source vertex is 1, so we altered every edge so that it points to 1, like this. And so here's some extra notes down at the bottom. The graph and adjacency list implementation is provided for you. Assume no null inputs, and as well as a note on how to define like a graph object. And then the graph you'll be given is always connected, and you are also provided a directed graph class as well. So you have a regular graph class and a directed graph class. And then as well as the bottom, here's the method that you will be implementing. So, yeah.
Sorry, I'm just gonna read everything over again.
Yeah, no problem.
Okay, so I'm thinking I take the input vertex and I find everything that points to that, and I make like 2 and 3 point to 1, and then I can recurse back. So
Okay, sounds good.
then, okay, V is the input. Okay, yeah, it's an adjacency list, so I'm gonna get everything that points to 1. So I'm gonna do a for loop to get everything it's adjacent to. So I'm gonna get a vector to store the edges. And then I'm gonna use a queue to go through the adjacency list.
Okay.
So first I'm gonna push the source. And I'll keep track of the current node we're on by taking the front of the node. And I'll get rid of it.
I mean, you can take a load drink, right? Oh my god, the stench.
So I'm gonna go somewhere more quiet. I'm gonna pause the recording.
Oh, I love the
Okay.
Is this enough? Yeah.
Okay, so I'm going to iterate through this while the queue is not empty, and then while the loop is processing, I'm going to push what the source points to. So while the queue is not empty. And then I'm going to have to keep track if we've already seen this node. So I'm going to make an undirected graph to keep track of that. With the key being the node, and then it'll say true if it's already been visited. Then I forgot to create a directed graph instance. So if this node has not been visited, so visited, and then count, we'll check if it's in the undirected graph. So if it's not in the directed graph, then it will add it to it. So I would be the source, and then cur would be what it points to. And then I'm going to mark I as a visited. And I only need to add it to the queue if it's not visited, so I'll move this down here. I think this is it, but I'm just gonna go through it. So I created a instance of a directed graph. I created a queue. I don't need this vector anymore. That's within the directed graph class. And then I have a graph to, or undirected map, to store if the node is visited or not. And then I push back the source. And then while the queue is not empty, I make the current node the node that's at the front, and then I pop it from the queue, and then I go through all the things that the source is connected to. And if that node is not visited, then I add it to the adjacency list as I being the source and cur being what it points to, and then I mark it as true, and then I push it back. And then at the end, I return the instance of the directed graph.
Okay. So how about you walk me through a test case? So come up. So just like you showed me your solution here, how about you try to think of edge cases and test cases that your solution could solve, and walk me through them, basically.
So like this case up here?
Yeah, it doesn't have to be like that case, just like any case, kind of just like, yeah, so just use this case and like kind of just like using a concrete example, just kind of like show me, like walk me through,
Okay.
like how, if you were testing like this code on your own, how would you like go about testing it and stuff like that to make sure your solution like works?
Well, I would check a undirected graph like this one. So I guess I can walk you through that. So this graph is one of the parameters and one is the source. So I would be pushed to the queue. And then we would, oh, I see, I forgot to mark the source as visited. So I'm gonna add that in. So one is added to the queue. Okay, this is supposed to be current right here. So one is added to the queue, it's at the front, it becomes the current. and then we go through all the things that 1 points to, which is 2 and 3, and they are not yet visited. So 2 will point to 1, and then 2 will be marked as visited, and it will be pushed into the queue, and then it would go to 3. 3 would be added to the adjacency list. It would be marked as visited, pushed to the queue. And then at the front of the queue, would be 2. It's popped. We go through all the things it points to, which is 4. So that's added to the adjacency list. We push back 4, mark it as true. Let's push the queue, and then next in the queue would be 3. We go through all the things that points to 3, which is 4 and 5, but 4 was marked as visited. So then we go to 5, we add it to the adjacency list, mark it as visited, push it to the queue. Next at the front of the queue is 4, which points to 6. So we'd add that to the adjacency list. 6 pointing to 4, mark 6 as true, push it, and then we're back at 5. 5 points to 3 and 4, but those have already been visited. So then we go to 6, and then 6 points to 4, but 4 has already been visited. So then the queue ends, and we return the directed graph.
Okay, so is this your final implementation? Are you done?
Yes.
Okay, so, okay, good. So I'm gonna give you some feedback now. You basically did a really good job implementing the solution. Pretty much everything is like, you have like very much the right idea. But I'm gonna give you more like feedback right now on in terms of like interview skills, and then I'll give you like the solution at the end. So you did like a good job, like kind of walking me through the like your thought process. The only thing is that I wish you would have like spoke a little bit more, because I felt like you said like I'm going to do this, and you didn't really give a reasoning why. Like you walk through like step by step what you're gonna do, but I feel like you could have put a little bit more in there to kind of just like give the reasoning why you're doing that, and not just saying like, oh, I'm gonna do this, because it kind of just shows like the explanation kind of just gives the like interviewer a better understanding of like your thought process.
Mm-hmm.
In addition, I also think that you also could have just like in general given a better, like, how do I say this, like a better, like more, I would just wish you would have like talked a little bit more. Yeah, you also, I assumed that you like understood everything, so you didn't really ask a lot of questions in the beginning of the interview, like about any constraints or anything. Additionally, towards the end of the interview, at least for like in terms of this assignment, it's good to like give test cases. So like when you're done with your like implementing your solution, it's good to like on your own just like describe to the interviewer like what you're gonna test, because it kind of just like solidifies like your solution. Yeah. So let me see. I'm looking at my notes here. So yeah, I just feel like more talking would have been better. to kind of just like explain to the interviewer like your thought process, and also explain to the interviewer that you have like a critical thinking map as well, if that makes sense. Let me see. But yeah, you did good, so good job. And yeah, so in terms of this, like the solution to this problem, you did a very good job. I would say probably there are some like differences in like that, or I believe some flaws in like the technicalities of like how you define certain things, certain objects and variables. Let me see. So well, I can just explain like the solution. So basically you did basically like something very, very similar to like the solution that I'm referencing. So you could have also created like a vector of edges in general, because you were given an edge struct. And so with this vector of edges, as you go through and do a breadth first search on this graph, you basically kind of just like switch the edges and then push it into this vector. And so whenever you're done, you can create a new directed graph. And all you need to do when you create this new directed graph is just like pass in the vector of edges, the new vector of edges, as well as the size of the excuse me, how many. You can also pass in the amount of vertices in the graph. So you very much had like a very good solution. You did a breadth first search, which is basically the general gist of this problem, is to do breadth first search. And then you had a queue, which is good, as well as a map. Let me see. Yeah, a map. You could have also used a vector, but you did like, you had that's also correct. And then so yeah, I mean, do you have any like further questions about anything?
No. Wait, what did they use for the vector to keep track of visited?
They just used like a vector of booleans, and they created it, like they initialized it to be like the size of the amount of vertices. Yeah.
So then what? Oh, okay, that makes sense.
Yeah, and so basically, let me see.
It's probably the same access time because undirected map is constant access time.
Yes. Yeah. So, but yeah, so I can like send you the link to the solution when we're done, if you want. But yeah, you did a good job. If you want to like compare your like exactly your solution with the answer. But yeah, so that's all my feedback I had for you. Yeah, so I think we're done.
Yeah, I think so.
Okay.
Thank you.
No problem.